Have you ever really stopped to think about the stuff that makes up our world? I mean, everything we see and touch is matter, but it shows up in some really different and fascinating forms. So today, let's dive into the amazing states that everything around us can take.
Okay, so take a look at this. Right off the bat, we see a solid. Something like a diamond. It's hard, it's got a fixed shape. And then there's this, a liquid. It just flows, right? It takes the shape of whatever you pour it into.
And finally, we've got a gas. It's just everywhere. It expands and fills up any space it's in. So you've got three totally different behaviors, but here's the kicker. They're all made of the exact same fundamental stuff. They're all just matter.
So what's really going on here? Why does it feel like your car tire is going flat on a really cold morning? And on the flip side, how does just heating up the air inside a huge balloon make the whole thing float up into the sky? Well, the answer isn't in what we can see with our own eyes. Nope. It's hidden away in the secret, invisible world of molecules and the energy that gets them moving. To really understand this, we need to zoom in, way, way in. Welcome to the world of molecules. And this right here, this reveals the secret. So in a solid, the molecules are packed super tight in a fixed grid. Think of it like fans in stadium seats. They can jiggle around, but they can't really go anywhere. In a liquid, it's more like a crowd on a dance floor. They're still close, but they can slide past each other. And a gas? Oh, they're like players on a soccer field, just zipping all over the place with tons of energy and space.
This table basically puts some numbers to that idea. Just look at the kinetic energy row. That's the energy of motion. For solids, it's practically nothing. For gases, it's the highest. And you see the same story with motion itself. Solid molecules just vibrate. Gas molecules, they're rotating, vibrating, and flying all over the place. It's this core difference in energy that gives each state its totally unique properties.
Now, gases might seem totally chaotic, but it turns out those super energetic molecules actually follow some really elegant and predictable rules. So let's check out the laws that keep them in line. First up, we've got Boyle's law, and it's actually pretty simple. If you keep the temperature the same and you squeeze a gas into a smaller container, its pressure goes up. It's a perfect inverse relationship. As one goes down, the other goes up. And here's what that looks like in action. On the left, you've got some gas at a certain pressure. But then, on the right, we double the pressure by adding another weight. And look, the volume gets cut exactly in half. Those molecules are just forced closer together, so they bang against the walls more often, and that's what pressure is. And if you plot that relationship on a graph, you get this beautiful curve called a hyperbola. See how as the volume along the bottom gets smaller, the pressure on the side just shoots way up? It's the perfect picture of that inverse relationship. All right, next is Charles's law. This one looks at the connection between volume and temperature, but this time we're keeping the pressure steady. And it's simple. You heat a gas, it gets bigger. They go up and down together. So why does that happen? Well, when you heat the gas, like from 200 to 400 Kelvin here, you're giving those molecules a massive energy boost. They start moving way faster, they hit that piston with a lot more force, and they literally push it up, doubling the volume. This is exactly how a hot air balloon works. So when we graph Charles's law, it's just a straight line. It shows for every little bit you increase the temperature on the bottom axis, you get a proportional increase in volume on the side. A perfect direct relationship. So simple. Okay, so those gas laws are awesome, but they describe a perfect or ideal gas. And in the real world, things are, a little bit messier. So let's look at the difference between the neat theory and the slightly chaotic reality. So an ideal gas is really just a concept we use in physics. It imagines that molecules are just tiny points with no volume, and that they don't attract each other at all. Real gases, though, they're made of actual molecules that take up space and have these little forces of attraction between them. Now, most of the time, at high temperatures and low pressures, it doesn't really matter. But when you start to cool a gas down or really squeeze it together, that's when you start to see real-world behavior drift away from those perfect laws. To measure how much a gas deviates, scientists use something called the compressibility factor, or Z. Okay, now really look at this graph. For a perfect ideal gas, Z would always be exactly 1. That's that straight horizontal line you see. But check out the curves for real gases. At lower pressures on the left, those little attraction forces actually pull the molecules together, making them easier to compress than ideal. So their Z value actually dips below 1.
But then, as you crank up the pressure, the physical size of the molecules themselves starts to get in the way, making them harder to compress. And that's when their z-value shoots up above 1. It's such a cool picture of how messy reality really is.
So, we've gone on this whole journey, from the big world we see down to the tiny molecular level and back again. But why does any of this actually matter? Well, it turns out these invisible rules have a huge impact on our everyday lives. Boyle's law? That's absolutely critical for scuba divers. They have to know how pressure changes the air in their tanks and their lungs as they go deeper. Charles' law? Well, we already talked about it. It's what makes hot air balloons fly. And another one, Gay-Lussac's law, is why pressure cookers work. When you heat gas in a sealed pot, the pressure skyrockets, which lets the water get hotter than boiling and cooks your food way faster. So the next time you see a hot air balloon floating by, or you go to check your tires on a cold day, you'll know the secret. You'll get what's happening. It's this invisible dance of molecules, all following these elegant, predictable rules. So the question is, now that you know these rules, what else in your world do you see a little bit differently?